All right, so I think we're live here. All right, so before we start today's discussion, I would just wait for just one more two more minutes so that more of you can join today's class, and then we're going to start the discussion here. I hope you are all doing well, and again, good morning to you all. So we ended the last class with the discussion on block diagram reduction, block diagram algebra, right? And today we are going to actually learn a technique that can allow us to do whatever we did with block diagram algebra in just a single step. So this is a single step systematic solution to what we actually did in the last class. So in block diagram reduction technique, when we applied block diagram reduction technique in order to simplify our model, we required kind of a manual way of thinking about it and figuring out how to or what to do about the particular circuitry, right? But here we are going to learn that we can actually apply uh, a series of standardized techniques. Okay, so standardized rules, and then we can actually simplify and figure out the entire transfer function of the whole thing. We won't need to figure out things by ourselves. Okay, so there will be a certain set of rules, and if we can apply those certain set of rules, we will end up with the transfer function of the whole thing. So we would end up simplifying the whole thing. Okay, so that's why this signal flow graph, the idea of signal flow graph, is pretty important. Okay, so let's get started. So again, before we start, recall that the block diagram we talked about, or rather we simplified in the last class, was this one, right? So this was the block diagram reduction we did in the last class. All right, so I believe you can recall that. So we're going to start from this point. Okay, just keep this in mind. This was the example we did in the last class. All right, and today we're going to learn how to actually convert this block diagram into an equivalent signal flow graph. I'm going to explain what signal flow graph is, and then I'm going to teach you how to actually convert this into a signal flow graph. And let me tell you very clearly, uh, quite often, if you have a complicated system, if you want to describe this or describe the model of a complicated system, it is often beneficial or more useful to describe that complicated system through a signal flow graph instead of a block diagram. Often the block diagram becomes cumbersome to draw and cumbersome to analyze. Okay, so quite often, if you have a complicated system or complicated structure, to describe it in this kind of ways, it is better to use the idea of signal flow graphs compared to block diagrams. So it's quite easier often. And as a matter of fact, all the software that you use to actually solve this kind of block diagrams, like MATLAB, like the control package in Python, okay, like Scilab, they internally convert everything into a signal flow graph. Okay, all these systems are converted into a signal flow graph, and based on that, all the calculations are done. So even if you are not doing a signal flow graph yourself, the computer actually is converting all those systems, models that you construct using those software into equivalent signal flow graphs. Okay, because once again, in this technique, you will learn certain systematic way of solving it. And whenever you are programming something, okay, whenever you are writing a program to solve the structure of a complicated system, you would want something that is systematic. Because if something is not systematic, you won't be able to write a program for that, right? That's why signal flow graph is so important and it's so commonly used instead of block diagrams. Okay, and once you learn signal flow graphs quite well, then it will pretty much appear to you is that learning how to reduce block diagram was futile. Okay, it would appear to you as such. Okay, so again, once again, we are going to talk about signal flow graphs briefly, what those means, what those are actually, and then we are going to talk about how we can actually use this in this context. All right, so let's get started. So what is a graph? Now you might think that, okay, I'm talking about something like a plot of something, but graph in the context of mathematics has a specific meaning. Okay, graph in the context of mathematics has a very specific meaning. Okay, so graph, the minimum, bare minimum, consists of something called nodes. Nodes. Okay, so this is a node. Node is a point. Okay, essentially a point. And say we have two nodes. So one node and another node. Okay, nodes are also called vertices. So this is vertex 1, or this is vertex 2. Okay, so nodes or vertices, and then you have certain connections between those. You have certain connections between those. So this is in mathematics what is called a graph. Okay, graph, whenever we say graph, we are not talking about plots. Okay, we are talking about something like this, a depiction of the connection between nodes, for example. Now these nodes could be cities. This could be city number 1, this could be city number 1, this could be city number 2, and this link can be a road between those cities. Okay, a way in which you can travel from one city to another city. Yeah, these problems arise like that only. Okay, so again, just call them nodes or vertices. So node number 1, node number 2, we have two nodes here. All right, so we have two nodes. So let's call them with certain names. Let's call this node number 1 V1, so stands for vertex number 1, and let's call this V2. So we have a connection between these two nodes. Okay, and this is the road, just like that. Okay, now of course these roads would probably have certain, what should I say, certain characteristic to it. Maybe imagine this is the city and this is another city. Okay, now there are, say, there is a, essentially there is a connection between these two cities. So there is a way in which you can travel from city number 1 to city number 2, right? Now of course, maybe this is the way, this connection is showing you a way in which you can travel by air. So you take an aeroplane and you actually travel with an aeroplane, right? So travel by air. So under that circumstances, so maybe your ticket or the cost of traveling would be something like, say, 5,000 rupees. Okay, so the cost of traveling would be, say, 5,000 rupees. Okay, so you are traveling in this way and your cost of traveling was 5,000 rupees, right? All right, understandable, quite understandable, not difficult, right? Now there are other possibilities. So you might travel by road, maybe. Okay, so when you travel by road, maybe in order to reach city number 2 from city number 1, you would have to go through city number 3. Okay, you have to go through city number 3 when traveling by road. So in that sense, I can say, okay, there is a connection between these as well. So you have to first go through this and then this. Okay, now of course, if you travel by road, the cost would be different maybe. So traveling by road in up to city number 3 costs you maybe 1,000 rupees, and here it costs you, say, for example, 500 rupees. Okay, so something like that. So now you can see how you can travel from city number 1 to city number 2, and this points, your starting point or destinations. These are the nodes or vertices. Okay, and here these connections are essentially the edges. So those who are joining late, somehow you can always go back to the lecture and watch the first part. But so far we are discussing how we can actually, what a graph is. Okay, what a graph is, and graphs are essentially a depiction of the connection between different nodes. So essentially it's not a plot. Okay, so there are nodes here or vertices, and if we depict the connection between them, so it's a graph then in the mathematical context. So this could be other things as well. Okay, this could be computers, say V1, V2, V3, they are computers, and these lines are how they are communicating with each other. Okay, just to show you what I mean. Okay, I use a Linux computer just to show you what I mean here. Say so if I do this, I don't know whether you can see this. If I run this, this will tell me give me some information. What information it is giving me currently is that, see, I am trying to look up google.com. Okay, so I am trying to visit google.com. So if I try to visit google.com, the response will come from Google's servers, right? But the response will not directly come to my computer through Google server directly. Okay, it will actually hop through quite a few different computers, different servers. So my computer is directly connecting to my router here. This router is connecting to the network switch placed outside. Okay, and that is connecting to the local ISP's server. Okay, local internet service provider server. Then that computer is connecting to another computer. Okay, the main server of our local ISP. Then that computer is connected to another computer, and that way, that connection that I originally sought, okay, from google.com was traveled through these many nodes. So it reached the google.com. So when I actually wanted to visit google.com, my request that I wanted to visit google.com actually traveled through 10 nodes here. So this is my gateway. So this is my router. Okay, the connection started from my router, started from my computer, and it actually then went to the router, then went to the local ISP, and all this way it took 10 nodes, 10 hops essentially, 10 computers. Okay, it hopped through 10 computers to visit google.com. Okay, so this was the final destination IP of google.com, for example, here. Okay, and it took 10 hops here. Okay, so that is a graph. So essentially all the computers that are in this thing, okay, in this connection, throughout this connection, are all constructed as graphs. You can imagine all the computers are nodes essentially, and the connection are depicted through lines, graphs. Now you can imagine if you run this on your computer, or maybe if I run this later on today, okay, these connections, this information will be different. Okay, so if you do this yourself, you would see that the information is different for you. Okay, because whenever you are trying to visit google.com or any other website for that matter, okay, the connection through which you receive the data will be through a different set of computers, right? Yeah, traceroute is a standard Linux command that actually traces the route through which the packets actually go, right? And don't worry about that. Okay. So the point is the Google servers. There are several Google servers, right? But when you try to visit google.com or, for example, any other website, okay, so it's the job of that server, for example, to figure out what is the fastest route to your computer. Okay, and there are so many algorithms along the way that figure out what is the fastest, most efficient way of reaching you. Okay, so that's again a part of the algorithm. Yes, no, it does not always try to follow the less number of nodes, but it always tries to find out the most cost-effective way. Okay, so here in this case, the cost is equal to the amount of time it takes to reach you. Okay, so the fastest way could be through multiple hops, but it could still be the fastest, right? So again, there are so many counterintuitive things here, but the point being, all these have certain costs associated with it, right? So if I ping a certain website, I will see that the response takes a certain amount of time. Say, for example, I ping google.com, say. You see, the response is taking a certain amount of time, 64 milliseconds, for example. Okay. So this actually tells you that, okay, all these hops. So when I pinged google.com's Google's website, so it was pinging this IP address. And again, if you do this yourself, this IP address will be different for you. Okay. So the thing is, when I pinged google.com, so it was pinging this IP address. But of course, in order to reach this IP address, it took these many nodes for the signal to travel through, right? All these nodes for the signal to travel through. But it still managed to get through to me, get back to me. So it went there and went back. Okay, yeah, ping. Ping is essentially pinging a server, essentially sending a small packet to the server to check whether the server is alive or whether the connection is available. So that packet went up to the Google server and came back with the acknowledgement that yes, it was successful to reach that, and all that took only in the entire process, all these hops, 10 hops. So it went there and the acknowledgement came back. Okay, all that took only 64 milliseconds. All that took only 64 milliseconds. Now, you know, for example, this is my gateway. So this IP address here is my gateway. So gateway is the router here. Okay, the router that is right next to me here. Okay. So now if I ping that instead, okay, so if I ping that instead, ping my router, you will see that it is taking significantly less amount of time. So if I ping my router, you see that it is taking significantly less amount of time, like point something millisecond. But when I wanted to reach Google server, it took me 64 milliseconds because it was going through all those nodes. Okay, but here when I'm pinging my router here, it is only taking me less than a millisecond. So of course there are no hops, just the next node from my computer here. You understand what graphs are, right? So graphs are essentially connections between nodes. Now these connections can be unidirectional, could be bidirectional. Okay, so if the connections are bidirectional, we don't put the arrows here. Okay, we don't put the arrows here. If the connections are bidirectional, okay, someone is saying can't understand the ping process. Actually, this is not something you don't have to understand in the context of this class. Just try to understand that this ping for this program, this is also available in Windows. This ping function here, or the ping command, actually sends a packet to the server that you designate. So this is a server, for example. This is a computer or a router, or could be anything, any server that's up on the internet. Okay, you can actually send a packet to this to check whether this server is up. Okay, maybe you have seen your internet service providers do that to check whether a server is up or not. Okay, or whether you have an active internet connection. Okay, so if you don't have an active internet connection, or if this server is not up, the connection will fail. It will say that it timed out, it failed, the connection failed. Okay, so yeah, it is actually showing you the connection between all the nodes. So essentially there are several nodes here. So several nodes, these are all computers. Okay, and all these computers are connected through many different ways. There are many possible connections between all those computers. Okay, many possible connections between all those computers. Okay, many possible connections, okay, through all these computers. So maybe this is your source node and this is your destination node. So starting from this computer, you want to visit this computer. Okay, so along the way, some algorithms will try to figure out what is the fastest route from your place to the destination, from the source to the destination. Maybe this is the fastest route to your destination. So all these other computers, you could have connected through all these other connections, other possible connections, but maybe your algorithm would choose this fastest possible connection. So these are again certain things about graph theory that we can talk about, right? So any confusion with this? So graph theory is a very essential part of mathematics, and as a matter of fact, you will see, yeah, I believe you have studied how to solve electrical circuit using graph theory, right? I believe you have seen how to solve electrical circuits using graph theory, right? So again, you can actually convert an electrical circuit into a network graph essentially. Okay, and from that you can actually you haven't studied. Okay, surprising to me. Okay, but you should have studied how to solve these. So how many of you are familiar with the software PSpice? How many of you are familiar with the software PSpice? Okay, just to give you a background idea, in that case, I can actually arrange an additional class for you. I mean, this is an important part that you should have studied in your circuit theory classes. Okay. So if you actually construct a circuit through PSpice or any other Spice software, okay, for that matter, and solve it using that software, what it does internally, it converts the circuit into a graph. Okay. So it converts the circuit into a graph. Okay. And then it tries to apply the algorithms. So the idea is very, what should I say, convenient for the computer. But you would see that doing the conversion into a graph and then solving that as a whole in circuit theory, it is very difficult for us human beings who would have to deal with long, pretty big matrices and all. But again, those are not an issue for computers. So anything that is systematic is good for computers. Okay. So that way, doing signal flow graphs is also good for computers. Very easy for us to actually write the programs. Okay. So that's what graphs are essentially for you. Okay. So just to give you one more information. So if there are two nodes, for example, node number 1 and node number 2, and if there is a connection between those, okay, the connection could have a weight. So this cost of going from one node to another, say, is called a weight. Okay. This is called a weight. Okay, right? And That's it. So that is all you need to know, for example. Okay. So if this is unidirectional, so if you can only travel from node number 1 to node number 2, then there is an arrow here. Okay, that indicates it's a unidirectional graph. So this kind of graphs, wherever you have arrows in the graph depicting that you can only travel one way through some of these, it becomes something called a diagraph. Okay, stands for directional graph. Digraph. Okay, it becomes a directional graph. All right. So that is something you need to understand. All right. So now comes the question of converting this block diagram into a graph. All right. So let's do that, because that's what we sought to do in this class. Hold on. That's what we wanted to do in this class, right? All right. So now look very carefully. So we have certain things that we need to understand here. Okay. So what are those certain things? These certain things are points where signals emerge or signals merge. Yeah, wait, WAIGST. We said weights of the paths or the connections. Okay. The connections are called edges. Okay. So if you have a graph, so you have nodes. You have nodes. Nodes are depicted with node numbers, and node number v1, node number v2. Okay, the connection is called an edge, and if it has an arrow direction essentially, then it's a digraph. Okay, and if it has a weight, if it has a value on top of it, so that's kind of the cost or something like that. The length, it could be the distance, it could be the cost. Okay, so it's called a weight. So these are nodes. Okay, nodes. So these are all node. Okay, so this is an edge, and this is the weight of the edge. Okay. This could be the cost, this could be the length, this could be the distance. Okay, this could be the time that it takes. Okay, it could be anything, it could mean anything. All right. So essentially, nodes are places where these. So see, this thing could also represent a signal, right? It could be representing a signal that is traveling, just like I showed you the traced out signal, traced out command that shows the packet, how the packet travels, the network packet actually travels through the network. Okay, we call it a network. Okay, graph theory is also called network theory. Network theory is also known as graph theory. Rather, I should say graph theory is also known as network theory. Okay, so essentially, whenever we use the term network, we essentially talk about nodes and connections between the nodes. Okay. All right. So if anybody from outside is joining, so welcome to you all as well. So try to follow along with us. So all right. So that's understandable, I hope, right? All right. So now again we are talking about, so we can say that this is a connection, and we can consider this connection to be a path for the signals to travel as well, right? It's a path for the signals to travel. Okay, so whenever signals merge or signals travel from a node, we consider that to be a certain viable option for a node. For example, you will see that this is the point. Okay, this summing point here, or whatever the comparator here. Okay, that's a point where the signals are merging or signals are emerging. Okay, from that. So certain signals are merging and certain signals are emerging from that. So that's a viable point to consider, to be considered as a node. So let's consider this to be a node. So let's keep that in mind. So we are considering this to be a node. All right. Similarly, we have another point here from which connection signals are entering and exceeding as well. All right. So signals are entering here. Again, signals are going out of that as well. So that's a viable point here where these kind of things are happening. Similarly, this is another viable point where signals are once again merging and emerging, right? This is another viable point where something like that is happening, and this is another viable point where something like that is happening. All right. So you can actually follow along. Try to follow along. It might not be difficult. Okay. So all the videos are already up on YouTube. If you face some difficulties, you can actually go back and watch the previous lectures. All right. And we always talk about the starting points and end points, right? Starting points and end points. And let's just say we have a starting point here and we have an end point here, and then that's obvious, right? So in our first class, we discussed that yes, this is the reference signal, and this is the signal that I want to appear in the output. So reference signals are also the desired output, and this is the control variable, the output of the entire system, final output of the entire system. So you see that we have identified all the vertices or all the nodes in the circuit or in this system. So is there any confusion or anything you might want to ask here, or anything I might have skipped? So we have identified all the nodes in this system. If you think we haven't, or if you have anything to add, you might want to tell me right now. All right, so that's fine, right? So let's do one. So let's do this then. So what we are going to do right now is that we are going to actually just hold on. What? Let's bring this back down here. All right. So let's draw these things here. Okay. So we're just copying and pasting this. So all the nodes here, right? So we have a node here. We have a node here. So I'm drawing it, just making a one-to-one copy of this. I don't know how much you can see. Let me just get rid of myself. All right. So is that fine? So these are all the corresponding nodes here that are representing the possible endpoints of the signals. Okay, yes, R is the input node. Yes, you are absolutely correct. R is the input node, and this is the output node. C is the output node. Okay, so of course we talked about that, right? So again, when I showed you that first out here, I had an input computer and an output computer, for example. Okay, I wanted to visit google.com, so I started from my own computer and it went through all the hops, okay, and finally reached Google's computer. So my computer is the input node, for example, in that graph, and Google server, that particular Google server, was the output node for that matter. Okay, so here, so my computer is the input computer here, and through all these hops here, I actually reach Google's computer, Google server, for example, and that's the exit node or the output. Okay, so this is often called the entry node. This is the entry node. This is also sometimes called the exit node. So entry and exit. Okay, so this is the entry node. This is the exit node. So entry node is the input and the exit node is the output. All right. So not a problem then, I guess. All right. So with that being said, so we have constructed an equivalent one-to-one picturization of whatever we have there, right? And now what I can say, I can actually depict the connections between them as well. You try to see this thing and then try to understand this properly. Okay, you might get confused at certain points. So this is R. I can depict it as R, and this is C. Okay. Now, of course, a signal is traveling from R to this node. You see, a certain signal is traveling from R to this node in this direction. So is this depiction correct? So if this is a node or this is the vertex, if this is the vertex, then a certain signal is traveling from R to this vertex, right? So that is what is the depiction here. Okay, this is the node, and there is the connection between that. So someone is saying one node is missing. What is that node? Have I? Okay, yeah, you are correct. I have missed one node, right? The last one. Yes, you are correct about that. Thank you for correcting, which indicates that you are actually following properly. All right, as I was saying, so there is a connection between R and this node, right? R and this. So, and that signal is traveling directly from R into this. Any confusion? I don't think any, right? Now, Now something is going into this from below, something is going into that node, this node essentially from below. But I don't want to talk about this right now. Okay, but let's keep a provision for that. Something is going into this from below. Okay, so let's keep a provision for that. Remember that something is going into this from below. Okay, but something is now coming out of that. So whatever signal is coming out of that is going into the next node. So I can actually draw once again something like this. So this is depicting, so this line is depicting that whatever is coming out of this node is going into this node. So similarly here I can see whatever is coming out of this node is going into this node. All right, no problem there, right? Now look at this and this, these two nodes. So whatever is coming out of this node is going into this node. Okay, whatever signal is coming out of this node is going into this node. But notice that if the signal X is coming out of this node, then what signal goes into this node? The signal that is going into this node is G1X. Of course, from the transfer function approach here, we know that. So the signal that goes into this one is G1X. So essentially this signal in a sense gets amplified. Of course, it gets amplified in the frequency domain. Okay, we discussed this in our second class, right? Lecture 2. So the previous lecture. All right. So this signal actually is going into this with amplification, right? So of course, here look very carefully that there is a depiction of a connection between these two nodes. Just hold on. All right, sorry for the interruption. And so we see that there is a connection between this node and this node. Of course, the signal that is starting from this point is actually going to this as well. And you see that there is a connection between that, right? No problem there. But the signal that is starting from this node gets amplified through this block here and reaches this. So if the signal here is X, then it becomes G1X. So there is an amplification here happening. All right. So let's put the arrow here. And on top of this graph, let's say we have a factor that depicts the amplification. So G1. So now essentially, as far as the graph is concerned, this value here, just like those numbers, this value here, G1, is indicating the amplification of the signal. Okay, just like it could represent the cost, it could represent the time taken, it could represent the length, it could represent many similar things. Okay, similarly here it represents the amplification. So the signal that starts from here and that goes into this point here, okay, gets an amplification by a factor G1. So if the signal is X here, it becomes G1X at this point. All right, so that is the factoring here. With that same understanding, on the previous nodes, we can to remove any possible ambiguity, we can just write 1 because they are not amplified. They are just traveling as they are. So R is traveling directly into this. So that gets an amplification with a factor of 1. So similarly, this signal travels into this directly. So that gets an amplification with a factor of 1. So whatever this signal is gets an amplification with a factor of G1 and gets into this, right? Similarly, whatever this signal is, so essentially at this point, whatever this signal is, goes into this one unaltered. So goes into this one and gets another amplification with a factor of G2 and then reaches this node. So if I want to construct that connection, depict that connection, so that becomes G2. All right, this connection becomes G2. So this connection becomes something that has an gain of G2. Okay, amplification factor or gain of G2, right? So these weights on the edges here in the graph are depicting the amplifications, okay, essentially. All right. Okay, someone is saying that there are in the previous note there are some changes in the input signal because something is coming out of that as well. We are going to take care of that. We are going to take care of that as well. Okay, because something else is coming into this and that's also going to be taken care of. So don't worry. All right. And now, right now, we are at this node. We are at this node. Okay. So whatever signal comes out of this node gets another amplification with G3 and reaches this node. So we are writing G3 here, right? And then whatever comes out of G3 node reaches the output node unaltered. Unaltered means it gets an amplification of 1. So no amplification, in other words. Okay. All right, not a problem. So we take care of the forward path, the entire forward path for the signal. Okay. Now let's take care of these. You see that here, out of here, for example, so this node here corresponding to this node. Okay. So why have I written 1 in the two starting nodes? I could have written nothing, but that might have been ambiguous. Okay, that might have misled somebody. So instead of saying that that signal, this signal, so can I say that there is a block here that has a gain of 1 here? Can I say something like that? Because that part is unamplified, right? That signal is unamplified. So I can say there is a block that has a value of 1, that has a gain of 1. Okay. So that is what we are saying here, literally. So if get through to it unaltered, we are just writing 1 here, so that there is no question of ambiguity anywhere. Okay, so that people cannot assume something incorrectly. All right. So you see, now look at this node here, this node which is depicting this one here. Okay, look at this node which is depicting this one here, and from that we also tap a certain connection. So this is a branch point, right? From this we have another transfer function through which we have a feedback, and that feedback is getting through this. So this signal that is starting from here, let's say this is C, okay, and that signal is becoming H2C, okay, and that is entering this node, right? But this is entering this node with a, you see, with a minus sign. So there is a minus sign here. So this is again a comparator. This is the feedback, right? Negative feedback. So it enters this node with a minus sign. So this is subtracted, not added. So in other words, we can actually make it a plus sign, turn it into a plus sign, and put a minus sign here. That would also do the exact same thing. Okay, we can put a plus sign here and write a minus sign here, and that way the signal that enters this point would be minus H2C. So that way these two added will give you the same result, right? So instead of having a minus sign here and having a positive transfer function here like that, I could have a minus here, so that this signal is minus whatever that, and I put a plus sign here. So this becomes a summing point. What is subtraction? Subtraction is nothing but addition of negative numbers. That is exactly what we have here. Is that understood? So with that understanding, we can say, okay, now let's depict that connection. So we have a connection between these two nodes, and this is the direction of the signal traveling. Okay, so you see there is a connection between starting from this and going to this. So we have a connection from this to this, and the gain is minus H2. So let's write it this way. So the gain is minus H2. All right. So minus H2, right? So that way, what you see is that the signal that is coming out of this, essentially coming out of this, gets multiplied with minus H2 and gets added up here. Okay. So all these nodes, they can only add signals. These nodes can only add signals. They cannot subtract signals. Okay. So these two are getting added up here. So whatever signal comes into this gets added up here. So whatever signal comes from this direction and whatever signal comes from this direction gets added up at this node. Okay. So there is an important distinction here. So when you are tapping signals, it is assumed that there is no loading. So whenever you are tapping signals from this, it is assumed that there is no loading effect. So this does not change. So tapping a signal does not change the signal. So we are tapping this signal C out of this here. So that does not change the signal in any way. Okay, it remains C. So tapping a signal is not a subtraction. Okay, but when it comes back to a node, it gets either added or subtracted like that. So whenever I tap the signal out of this, it is not subtracted from this point. Okay, it is still there. Whatever signal there was, it is still there here. Okay, but whatever signal I tap out of that travels to this, okay, gets multiplied with minus H2 and adds up here. Exactly the way it is happening here. Is that understood? Right? So once you understand this, then try to understand this part as well. So we have, yes, it does follow the law of conservation, but you have to assume that these have zero loading effect. Okay, so these either have op-amps in terms of circuits. Okay, so essentially this is not drawing any current. This is just sensing the voltage and sensing the information there. You try to understand something important. So to understand something important. For example, how do you make a voltmeter? A voltmeter measures voltage, right? A voltmeter measures voltage. But in order to move that permanent magnet, so a voltmeter essentially usually is the classical voltmeter. It's a permanent magnet moving coil instrument, right? It's a moving coil instrument. So essentially whatever voltage appears, that moves the coil, right? That moves a certain coil. So higher the voltage, higher will be the deflection of the spring there, right? Higher will be the deflection. So that way, based on the deflection, you will figure out, okay, the voltmeter depicts that this is the voltage. But try to understand, in order to deflect the coil, in order to depict the voltmeter itself is consuming some amount of power, and by consuming some amount of power, it is dropping the voltage. Okay, so ideally you want to measure the EMF. Okay, but the moment you connect a voltmeter, some current is drawn by the voltmeter, and based on that some current is being drawn by the voltmeter, there will be a potential drop. So the voltmeter will always measure lower than the EMF, because the voltmeter itself is a load. The voltmeter itself is drawing some amount of current. Ideally, it should not draw any current. That's why we say an ideal voltmeter has infinite series resistance. An ideal voltmeter would have infinite series resistance. Why? It should not draw any current. But a practical voltmeter will always draw some current. That's obvious. Okay. So that's how the calibration is done. Based on how much current is drawn, and based on that, the calibration is done. Anyway, so I think this is understood. So idea is that it is drawing minimal amount of current, and it is only sensing the voltage or signal essentially. Okay, and it could be buffered with op-amps. So there could be buffering amplifiers here that are actually buffering the signal. So even if it draws some amount of current, it does not matter to the circuit. It's nothing. The signal does not change. Okay, the signal does not change. So that's kind of the idea here. So there are buffers everywhere. Buffers are essentially capable of delivering the additional amount of current required by the devices here without altering the voltage here. Okay, so assume that there are buffers here in all the tapping points here. Whenever I drop a signal, tap a signal from, I usually put a buffer, and that's a standard circuit, standard way of designing electronic circuits. Whenever you are trying to tap a signal from out of something, you always put a buffer so that the additional load can be held without dropping the voltage, dropping the signal. All right. So once again, let's get rid of me. Okay. And look at this point here. Okay. From this point, from this node, we are again tapping the signal, multiplying that with H1 and feeding it back to this node. Just like before, we can put a plus sign here. It's a negative feedback. We can put a plus sign here, and we can put a minus sign here. That would have exactly the same effect. So what I can do now, I can depict this in this plot. In this graph, I can depict this connection, right? So there was a connection between these, and the arrow is once again depicting the proper direction, and the gain is minus H1. Again, why is it minus H1? Because it is a negative feedback. So essentially the same idea like before. Yeah, buffers do not amplify the signal. Buffers provide the additional current required by the elements. Okay, so we will have a long discussion on op amps. Not a long discussion, but at least 2 classes worth of discussions on op amps and how to construct circuits based on that. Okay, how to implement transfer functions based on that. Yes, Shantanu is perfectly correct here. It compensates for the lack of energy. So whenever you put an op amp there, it actually compensates for the additional energy required to transfer a signal. Okay, in order to transfer a signal from one place to another, you need to transfer a certain amount of energy. Okay, and it compensates for that. Just to give you a very simple idea, so the standard outlet voltage in India is 240 volt, right? Standard home outlet voltage. Right? But the moment you put a load there, the moment you put a load in any outlet, it draws current, right? And by the very basic idea, you see that if it draws current, then obviously there will be a potential drop in the source. And that's true. The moment you start drawing current, there has to be a potential drop in the source. Okay. So whenever a signal is tapped, there has to be a drop in that signal. But in order to avoid that, we compensate for the additional required energy through an op amp, through a buffer. Okay. Op amp based buffer. The buffer does not amplify the signal. It only makes sure that whatever is whatever load I have connected, okay, is supplied with the proper voltage. Okay, load means current. In electrical engineering terminology, load means current. Higher load means higher current being drawn. Okay, so whatever current is being drawn gets satisfied through that through the application of a buffer. So buffer circuits will be everywhere whenever you are constructing a controller. Okay, so that the current limitation is properly held. Okay, so for example, if you are using a microcontroller to construct an electronic circuit or a control system, the pins in the microcontroller would have a current limit. Okay, so for example, 40 milliampere is the current limit, for example, on a pin. Okay, so if you are trying to send a signal to a device through that pin, okay, and if the device to which you are sending the signal is drawing more than 40 milliampere, what is going to happen? The microcontroller won't be able to deliver the current. Okay, the internal resistance will resist that. Okay, it won't be able to deliver more than 40 milliampere of current. And what will happen if I draw more current than that? The signal will drop, the potential, the voltage will drop. That way, the signal will become incorrect. Okay, the signal will become incorrect. So as long as I'm drawing less than 40 milliampere through that pin of a microcontroller, the microcontroller is happy, the signal is not dropping. Okay, so it has its own internal buffer, and that buffer is capable of delivering up to 40 milliampere. Now say you want to connect a device, okay, connect a device or send that signal to something that draws 1 ampere current. What will you do? You would put a transistor based amplifier, okay, that amplifies the signal in a way that the voltage does not change, but the additional current is taken care of. The amount of additional current is taken care of, and that's what amplifiers are, right? So maybe I am talking here right now, and I have a microphone, and then I have an amplifier, and I have a loudspeaker. So whatever I am saying here, that gets amplified, and you see that the loudspeaker, the sound is much higher in magnitude and everything. How that happened? The additional energy was introduced, but the additional energy that was introduced was proportional to the input signal. Okay, it won't be just a large noise or large bang. Okay, it would be additional energy introduced, but proportional to whatever input is coming through, whatever signal input is coming through. So that's the job of an amplifier. And if the amplifier has a gain of 1, okay, it's called a buffer. So buffer only compensates for the additional energy required. All right. So we got this connection depicted here. Okay, this connection was depicted here, right? And we have one last connection to take care of, and that's this connection. So there is a direct connection out of this from this up to this. Once again, we can write this as a plus sign. We can put a plus sign here, and here instead we can put a block that has a gain of -1. All right, it would have the exact same effect. Okay, so this signal here will become -C, and that will go here, and that will become R plus of -C. That's just R minus C. Okay, that was the intended goal here, and that is what we have achieved like that. So not having this and having a direct connection with a minus sign here, that's the same thing. So essentially C goes here, gets subtracted from R, so I get a R minus C. Okay, so if I want to depict that connection, let's do that. You know what, let me just try doing it my way. Just hold on, this is how I draw things often. And this is how I mess things up as well. Don't worry about it. All right, so that is the connection here, and that has a gain of -1. Okay, so this is what we have here. What we have here, that depicts essentially the same block diagram, but instead like a graph. So this is what we call the equivalent signal flow graph. In short, it's called SFG. Okay, one thing to note here is that in the block diagram, the important objects are these blocks. Essentially, that's why it's called a block diagram. It's a diagram all about the blocks. So G1 is a block, G2 is a block, G3 is a block, H1 is a block, H2 is a block. So block diagrams are all about blocks. So blocks are the most valuable players in this, right? Blocks are the most important things in a block diagram. But in a signal flow graph, signals are the most important things. Here, it's all about signals that are traveling throughout that. So it's the same representation in a slightly different way. Just like earlier you studied that the signals and systems, for at least for an LTI system, are equivalent. Okay, if you have a physical system at hand, or it's equivalent to having the impulse response of the system as well. Okay, so if you have an impulse response of an LTI system, it's equivalent to having the physical system with you. Right? So and here you see we have represented the same thing in two different ways. Here we are emphasizing the systems, the blocks. Okay, so that's why it's called a block diagram. And here we are emphasizing the signals that are traveling throughout that. So it's called a signal flow graph. They are depicting the exactly same thing, but here the MVPs are the signals, not the blocks. Okay, got it? The important things are the signals that are happening. Now, this kind of representation comes with a certain advantage. The advantage is that there are plenty of algorithms, plenty of theorems in graph theory that can now be directly applied on this in order to figure out that transfer function. So the transfer function is essentially C by R. Okay, the ratio of the output to that of the input under certain conditions. We are going to explain that those conditions in our next class. But that is what we calculated, right? So through a very tedious block diagram reduction in our last class, we calculated that the transfer function was this. In our last class, through a tedious calculation, we figured out that this was the transfer function, right? This was the transfer function. Now here we are going to apply a certain technique through which we are going to calculate the transfer function, but in a very quick and what should I say, in a very systematic way. Okay, so I'll give you just 2 minutes and I will ask you to figure out how many paths there are in this circuit. So in how many ways can you start from R? So imagine these are all cities, these nodes are all cities. Okay, question is, in how many ways can you start from this node here and end up at this node? Can you start from this city and end up at this city? Okay, the directions, the arrows show you the direction in which you can travel. Okay, and also tell me how many loops there are. Loops are essentially paths, loops are essentially a series of nodes where you start from one node and end up coming back to that node. So if I start from here and go through this and come back to this, that's a loop. Okay, so I will name the nodes. So this is node number R. So this is node number 1, this is node number 2, this is node number 3, this is node number 4, this is node number 5, and this is node number C. Okay, so through 2, 3, 4, and back to 2, that's a loop. Through R, 1, 2, 3, 4, 5, C, that's a forward path. Okay, that is another loop. So start from 3, 4, 5, and come back to this. Only thing is that whenever you are talking about a loop, you cannot travel the same road twice. You cannot travel the same road twice. You cannot go through the same edge twice. Okay, so now tell me all the loops. Please write down all the loops and all the forward paths that you see in this signal flow graph. I'll be back in a minute. All right, so it seems like many of you have actually given me the correct answers. Yes, many of you have actually given me the correct answers. All right, so let's get through to all of that. Okay. Yes, we are going to actually answer your questions. Someone is saying if there is something common about it, what then? Okay, we are going to talk about all that. So don't worry. So is it visible? Of course, I think it's visible because we just get the small one. All right. All right. So what is the forward path? What is the forward path? So in fact, there is just a single forward path in this whole thing. There is just a single forward path in this whole thing, and that's this. This is the single forward path. Okay, that's a single forward path. Yes, yes. I mean, almost all of you are correct here. Okay, so that's a single forward path in this. All right. So let's call this the forward path 1, forward path number 1. Okay, that's forward path number 1, and so let's say forward path for path number 1, forward path number 1, and when you travel to through that forward path number 1, what is the total amount of gain you encounter? What is the gains you encounter? So essentially forget about everything else. So if a signal started from this point and ended up at this point, what is the gain it faced? So it faced again G1, then it faced again G2, and then it faced again G3. So the gain it encountered would be G1 times G2 times G3. Okay, so I would say that the forward path 1 had a total gain of G1 times G2 times G3. Yes, I mean almost all of you are correct here, right? So that's fine, I guess. No problem there. Any confusion there in this one? That's your forward path number 1. Okay, so that's the only forward path you have in this. All right. Okay, now let's talk about the loops. Okay, now how many loops do you see? So let me see. We have it seems like we have one loop here. So loop essentially is starting from one node and coming back to the same node without traveling through any edge twice. Without traveling through any edge twice. So that's one loop. Okay, so we are starting from this and coming back to this. Okay, so that's one loop, right? That's one loop, right? Someone is saying no, sir. I mean, what is no, sir? I mean, can you please elaborate on what you are saying? So this is one loop, right? So this is loop number 1. Now, of course, your loop number 1 can be different from my loop number 1. Okay, but it doesn't matter. Whichever I am considering first or second, doesn't matter. So loop number 1. So this is my loop number 1. So we are starting from here, going back to this. So when the signal starts from here and goes through all that and comes back to this, what is the gain it encountered? It encountered a gain of G1, then it encountered a gain of G2, and then it encountered a gain of minus H1. So in total, it encountered a gain of like that, G1, G2, H1 with a minus sign. And that is something we call the loop gain. So gain of this entire loop. So the gain of this entire loop was G1 times G2 times minus H1. Okay, so this is the gain of this loop. So if a signal travels through this, it will in total get a gain of G1, G2 times minus H1. So G1 times G2 times minus H1. So essentially minus G1, G2, H1. Yeah, so yeah, you said no, so I was confused. Yeah, right. So if you have no doubt, please write all clear or something. So please give me an affirmative answer. That way I am absolutely sure that there is no ambiguity, just like these ones here. Okay, these ones are there to make sure that no one gets confused about anything. Okay, so please write affirmative or confirmed or understood. All right, so this is called the loop gain. So loop number 1 here has a loop gain of this. So L1 is considered to be loop gain. Here's for example, and this M1, why minus G? Yeah, minus G wasn't there actually. It was supposed to be G1, G2. See, the signal travels from, the signal is starting from this and going through all that, coming back to this. So it is encountering a gain of G1, then G2, and a minus H1. So the gain is essentially G1, G2 times minus H1. And that's why in total I have a minus sign here. Okay, it was G1 times G2 times minus H1. Okay, so this is the loop gain. And similarly, this is the forward path gain. So M1 is the forward path gain. So this is the forward path gain of path number 1. Got it? I think no problem there. So let's talk about the next portion here. All right. So do you have another loop? Yes, we have another loop. So let's talk about that. Once again, the order in which I am considering the loops might be different than yours. That's quite obvious, but it does not change the ultimate result. That's the important part. So this is the forward path, and this is the loop. So it is going in this direction and then coming back in this one. Okay, so this is loop number 2. Loop number 2. Okay, and loop number 2 has a gain of, you see that it is going through G1, G3, and then minus H2. Okay, G1, G3, minus H2. So this loop gain L2 is minus G1, G3, H2. So you multiply these, right? So whatever signal started here encountered a gain of G2, then a gain of G3, then a gain of minus H2. So this is the loop gain. Okay, so we have another loop, the last one, and that's the biggest loop here. Okay. So it actually starts from this point and comes back to this. So this is the biggest loop here, I mean biggest in terms of the loop, in terms of how it looks. So this is loop number 3. Loop number 3. Yes, you people have already gotten the correct answers. Okay, loop number 3 has a total loop gain of, what is the loop gain here? So you see there is a gain of 1, then G3, G1, G2, G3, and then there is a minus 1. So G1, so 1 times G1 times G2 times G3 times minus 1. So this is minus G1, G2, G3. Minus G1, G2, G3. So that's the entire gain of the this loop here. So this is the gain of this loop. And do you have anything else? So any other loops, any other possibilities? Is there anyone who thinks that there are other possible loops or something else apart from what we have done here? So we have 1 forward path and 3 loops. So apart from this, is there anybody who thinks that anything else is there? There are any other possibilities? So through all this, for any path, okay, for anything that qualifies as a path, you cannot travel the same road twice. You cannot travel the same edge twice. So in this, remember that we travel through all the edges only once. Here also we travel through all the edges only once, all these cases. So, and a closed path is a loop. A loop number, someone is saying loop number 2, G2, G3, H2. Yeah, sure, absolutely. What am I written? It's going to be G2, G3, H2. Yeah, sure. Why not? It's going to be G2, G3, H2. So minus G2, G3, H2. Yes, thank you for correcting me. So this was G1, G2 minus H1. It was G2, G3 minus H2. Yes. So minus G2, G3, H2. Right. You are absolutely correct. You are absolutely correct about that. So in this loop, yeah, it's going to be, the gains are going to be G2, G3 and H2 with a minus sign, of course. And here it's going to be G1, G2, G3 with a minus sign. Yes, you are correct. Thank you for correcting me. Now to give you the background knowledge out of this, the idea is that you can actually, with this knowledge, you can figure out the transfer function of the whole thing. How is that? So the person who invented this signal flow graph, okay, the person who invented this signal flow graph, his name was Mason, and Mason actually through certain theorems in graph theory, which I unfortunately cannot teach you right now. There are certain theorems of storm chains and certain flow algorithms, okay, based on which he calculated that the transfer function can be calculated with this formula, and I'm going to explain what this formula means, okay, through this formula. Now what this formula means, I'm going to explain shortly. Okay, so this is the formula for calculating the transfer function, and since this is the formula that was actually derived by Mason, it's often called Mason's gain formula. Okay, so there is a big derivation of this. I mean, the derivation takes about 1 hour to tell you, so that's why we are kind of skipping this, and also the derivation is not a part of your syllabus. But if you are interested in knowing where it comes from, where this result comes from, I can actually teach you that as well in some additional class that we can arrange. For the moment, assume that this is the transfer function. Okay, now this has certain background theories, other background theories of based on graph theory, okay, or network theory. So that is something we are skipping here. Okay. Yes, you are absolutely correct. Those who studied computer science, they definitely studied this, or rather, they should have definitely studied this. Okay, it's kind of graph algorithms. Yeah, there are several graph algorithms. So this is part of that. Okay, and in fact, whenever you are solving a circuit using a computer, solving any problem related to a network, circuits are also called networks, right? So this kind of theorems are implicit in many situations. So understand that this is called Mason's gain formula. Okay, and here this is what gives us the transfer function. Okay, what gives us the transfer function. And let me explain these terms here properly. Okay, let me explain these terms here. So m k, a k is kind of a parameter here, right? K is a, what should I say, index. It is like m1, m2, m3, m4, just like that. So mk is the index. So kth index essentially, m1, m2. So this is kind of like, you know what it means, right? So this essentially, just to give you that idea. So this essentially means it is like m1 delta 1 plus m2 delta 2 plus and so on divided by delta. Okay, it is just like that. So mk stands for essentially m1, m2, etc. So it is the gain of the kth forward path. Okay, so this is the gain of the kth forward path. So m1 would be the gain of the first forward path. Now, how many forward paths do you have? Forward path is essentially a path. Now, what is the path? In a so a path in a graph is essentially starting from one node and ending at another node, ending at some other node. Okay, but without traveling through any edge twice. Okay, so that's a path. Okay, and if the starting node and the ending node are the same for a path, it becomes a loop. So this is a path, and since it is starting from the starting point, entry node, and exiting at the exit node, so it is called the forward path. So there is only one forward path. So for our consideration, m1 is the only forward path. Okay, no problem there. So let's get rid of some of that. It does not flow away. Oh, really bad. Hold on. I thought it flows away. Just hold on. Okay, fine. We are fine. So mk is the gain of the kth forward paths. So that we are actually fine. I have not messed anything up. All right. So for our case, there is only one forward path, so that has a gain of m1. Right. Now, before I talk about delta k, let's talk about delta. Delta is the determinant of the graph. So graphs are essentially, graphs are represented with matrices. So in case you have studied graph theory or that part, that is called the graph theory, right? That's called the so essentially graphs can be represented through matrices. Okay, there are certain matrices called adjacency matrices. Okay, incidence matrices. So graphs can also be represented through matrices, and this delta is kind of called the determinant of the graph. Determinant of the graph. And again, I could teach you why these things are the way they are, and the formulas behind all these, but that would take a separate class by itself. But if you're interested, I can actually help you do that. So determinant of the graph can be calculated as with this formula: 1 minus summation of Li plus summation of Li Lj minus summation of Li Lj Lk plus and so on. What does it mean? It means this. This is 1 minus L1 plus L2 plus L3 and so on, plus L1 L2 plus L2 L3 plus L3 L1 and so on, minus triple pairs like that, triplets, L1 L2 L3 plus whatever similar. Okay, and plus dot dot dot. Okay, so that is what it is showing here. But what does it mean? Going to explain. That's how you calculate the graph determinant. Okay, so let's do the determinant here. Okay, let's calculate the determinant for our graph. So we already know the value of m1 for our graph, but let's calculate the graph determinant. Okay, for our graph, what is the graph determinant? It's going to be 1 minus. So how many loops are there? How many loops are there? There are 3 loops in our graph, right? L1, L2, and L3. So 1 minus L1 plus L2 plus L3. Okay. And these, what are these? What are these? Right? This summation of Li, Lj. This, if I explain this, so if I write this down rather, okay. So rather these parts, you know what? I might have to move this even further. This was a bad idea to begin with. Hold on. So now I believe I can actually bring this down. Not surprised. What is happening? It won't allow me. Hold on, okay. All right, no problem. And these things that we are writing here, these things, these quantities, these are sum of loop pairs, sum of non-touching loop pairs. Now let's write it this way: sum of non-touching loop pairs. Sum of non-touching loop pairs. Okay. Similarly, these here, I'm going to explain what I mean by saying this. These are sum of non-touching loop triplets. Essentially 3 non-touching loops, 2 non-touching loops. Okay, and so on. So what it means is that, and again, let me just explain this part as well, as we are here. So this is depicting some of the loop gains. So for our example, delta would be 1 minus sum of the loop gains. So I have 3 loops. So this is going to be L1 plus L2 plus L3. And then plus sum of the non-touching loop pairs. Now, non-touching loop pairs are loop pairs which do not share a common branch. Again, let me repeat. Okay. Yeah, I'm explaining the second summation term. Second summation term, so second term here actually representing sum of non-touching loop pairs. So if you have non-touching loop pairs, okay, then you put those terms here. So look at this. So imagine loop number 1 and loop number 2, they are not touching each other. Okay, loop number 1 and loop number 2, imagine they are not touching each other. If they are not touching each other, in that case, I would write L1, L2 here. Okay. If loop number 2 and loop number 3 are not touching each other, I would write loop 2, loop 3, this like that. But if loop number 1 and loop number 3, they are touching each other, that won't be appearing here. So any two loops that touch each other will not be appearing here. But what is the meaning of the term non-touching? Non-touching means the loops do not share a common branch. The loops do not share a common branch. So non-touching means they do not share a common branch or path or whatever. Basically a common branch here like that. Now look at this. Look at loop number 1 and loop number 2. Loop number 1, this is loop number 1 and this is loop number 2. Do they not share a common branch? Are they touching or are they non-touching? The answer is yes, they are not non-touching. They are touching in fact. Because this branch here, this branch here is in common. So essentially these two loops, this loop and this loop, they are touching loops in fact. So because they share a common branch. Okay. So this branch is common. Similarly for loop 2 and loop 3, this entire thing, I mean branch G2 and branch G3, this entire thing is common. Okay. So loop 2 and loop 3, they are also two touching loops. Similarly, loop number 1 and loop number 3, you see that this part in loop number 1, like this branch through G1 and G2 is common with loop 3, that this also has this branch with G1 and G2. So loop 1 and loop 2 in pair, they share common branch. Loop 1 and loop 2, they also share a common branch. And loop 2 and loop 3, they also share a common branch. So none of them are non-touching. So all of them are touching each other in a sense. Okay. So that's a loop, non-touching loop pair. So essentially we don't have any non-touching loop pair, and as such, we don't have any other terms. But don't worry, before ending to this class, I'm going to show you one example where you have non-touching loop pairs. Okay. And similarly, if there are no non-touching loop pairs, you cannot have non-touching loop triplets. Okay, triplets are combination of 3. Yes, absolutely. If the loops have no common gain term, then that means they are non-touching. Yes, that's correct. Absolutely correct. All right. But there might be a situation where I might give you a problem where the same transfer function appears twice. Like it has G1 and G1. Okay, both of them are the same transfer function. So that might confuse you. Okay. So this is the more concrete definition. So they do not share a common branch in a single program. So that's the gain for our particular scenario. So determinant of the graph. So that's the graph determinant here. So let's calculate the graph determinant. That's going to be 1 minus L1 plus L2 plus L3. Okay. So let's copy L1. Sorry. So that's L1. Let's copy L2. Let's copy L3. And of course, we have a bracket. That's the graph determinant. Right? And this is equal to 1 plus, as you can see, all that. Right? So it has to be G3, sorry. So that's the graph determinant, right? No problem there. That's the delta that we are calculating for this. Hold on just for a second. All right, so that's the graph determinant. Okay, so we have taken care of delta, and there is one more term. So delta k. So we have delta mk, and what about delta k? So essentially delta 1, delta 2, delta 3. So delta k is equal. So delta k is equal to delta considering only those loops. Again, delta is determined by the loops, right? Considering only those loops that do not touch the kth forward path. Okay, so delta k is equal to delta. Now you can only consider those loops which do not touch the kth forward path. In other words, in this example, I only have one forward path, so I would have delta 1. Okay, so I had m1 in this picture, I had m1, so I would have delta 1. But when I am calculating delta 1 would be equal to delta. Delta 1 would be equal to delta. Okay, but here I can only consider those loops. In this calculation, we can only consider those loops which do not share a common branch with the first forward path. Okay, so delta 1 would be equal to delta, but now in this calculation we can only consider, okay, those loops which do not share a common branch with the first forward path. Okay, that do not share a common branch with the first forward path. Okay, but let's see which are the loops. I have 3 loops: loop 1, loop 2, loop 3. I have to disqualify some of them, right? So let's talk about loop 1. Okay, this is loop number 1, and remember this is your first forward path, the only forward path here. So path number 1, forward path number 1, and this is loop number 1. Do they share a common branch? Yes, this shares a common branch. So this loop number 1 shares a common branch with the forward path. So it's gone. Okay, so it's you can actually ignore this one now. So it's disqualified. Okay, similarly here, this also shares a branch with the first forward path. So this is also disqualified, and this also shares a very big branch with the first forward path. So this is also disqualified. So all the loops are disqualified. L1, L2, L3, all of them are disqualified. All of these are disqualified. So what am I left with? I am left with just one. I'm just left with one. So in this, the result is just equal to 1. Since L1, L2, L3, all of them touch the first forward path. So if we had another forward path, in that case, I would calculate del 2. Similarly, I would have m1, m2. for that second forward path, and there I would have to calculate the value of delta. I have to recalculate the value of delta, and I would have to disqualify those loops which share a common branch with the second forward path. Okay, so that's the calculation for this example. Okay, and now it says that the transfer function is summation mk del k by del k. The transfer function, whole transfer function C by R, is summation mk del k by del, right? So now of course here I have only one forward path, so that's going to be just m1 del 1, and that's going to be delta. Now what is m1 del 1? Now what is m1? Let's go back. I know m1 is g1, g2, g3, and del 1 is 1. So this is just g1, g2, g3, and moments ago I calculated delta. So let's copy that and paste it here. So what did I copy? Sorry, that was not my intention. Okay, and that is going to be the transfer function of the whole thing. And you can actually verify this result. Moments ago, earlier, we actually copied this result from our last class. Let's copy this back here. Let's verify that we actually have the correct answer. You see G1, G2, G3 is matching up here. In the denominator, we have 1. 1 is matching up. So we have 1. 1 is matching up. We have G1, G2, G3. We have G1, G2, G3. We have G1, G2, H1. We have G1, G2, H1. We have G2, G3, H2. We have G2, G3, H2. And the numerator, I have G1, G2, H. Yeah. So it's exactly matching up with the result. So whatever we did earlier exactly matches up with what we have currently. So this signal flow graph technique might seem a bit difficult. Okay, might seem a bit difficult, and rightfully so. But the thing is, once you learn this technique well, it would seem that this technique is easier than doing a block diagram reduction. Okay, it would seem that this technique is easier than doing a block diagram reduction. Okay. Okay. As a very quick example, I won't be drawing all the things for that particular example. As a very quick example, I would take the exercise problem that I considered for in the last class, right? At a very quick next example, I mean. So let me just go back to this. Hold on. Yeah. So this was the problem, right? This was the problem that I wanted you to do as an exercise for the block diagram reduction technique. Okay. So this was the problem that I wanted you to do as an example of block diagram reduction, right? So I wanted you to do this, and instead of doing this with the block diagram reduction technique, which you have to do as your exercise problem, now let's do this using the technique of signal flow graphs. Okay. So that way you will see that it is much easier to do, rather actually construct signal flow graphs and solve it using the signal flow graph technique once you have actually learned this properly. So let's start. So this is one node, this is another node. Of course, this is the starting node. This is the starting, this is another node. Here is another node. Here is another node. Here is another node. But you see, these two nodes can be combined because essentially whatever signal comes out of this is tapped, right? So I would consider these two together. Similarly, these two can be also combined because whatever signal appears here is actually tapped out of this. So actually, no, yeah, let's keep them separate. It would be easier for anybody to understand. Fine. These are all the nodes, right? Also, do we need another node? No, no longer. Nothing else is needed. So yes, so if you have done this using block diagram reduction technique, congratulations. So you have actually learned something. Okay. Now let's construct the signal flow graph out of that. All right. So let me try doing that. So let me bring this. Okay. So these are the nodes that I have drawn. All right. Change of color. Okay. These are the nodes that I have drawn. So let's show the connections. So there is the connection here between these two. There is a connection between these two. There is a connection between these two. You see, I'm drawing it very quickly. And once you are comfortable with these things, it will be very quick to actually draw these things. Much easier than actually doing a block diagram reduction. Okay, all right. And let's talk about the connections here. I see that all the feedback loops here, right? I see that there is a connection here. So I will draw these and you just let me know if I make any mistake anywhere. You know, I'm really bad at drawing themes. Not there, not there. And okay, someone is saying, what about this point? What about this point here? What about this point or what about this point? I'm going to draw these, along all these, so don't worry. So I'm going to draw all these. Again. So there is the connection between these two. I hope I'll be drawing it correctly. I sincerely hope so. Okay, and there is another connection between these two. Okay, there's another connection between these two, and for that I will have see the amount of trouble I go through for drawing all these. Right, so that's also fine. Okay, I made a mistake, right? It wasn't supposed to be from here. That's a problem, right? Okay, and then we have another connection joining the likes of these. See, I could have actually drawn this at home and shown you the end results, but that way you won't get an idea about how much effort is needed in doing these. So I believe you need to have that idea. I think all the connections are now properly depicted. So if something is missing, please let me know. So let's put the arrows here. So we have an arrow here in this direction. We have an arrow in this direction. That's going to be G1, and we have another arrow here. That's one. That's one. Okay. All right. So we have another arrow here. That's one. We have another arrow here. That's G4. Okay. And we have another arrow here. That's one. Arrow here. That's G2. Okay, it is G3. It is going back, and that's a negative feedback, so minus H2, and this is minus H3, and this is minus 1. All right, so that's the signal flow graph for this. So that's the signal flow graph for this. All right. So that complicated structure that I gave you has this signal flow graph. All right. So let's quickly figure out everything that is there to know about it. All right. So just give me like 5 or 6 more minutes. I will be able to achieve. Hopefully, I'll be able to do all that. Okay. So how many forward paths? Let's see. So we have one forward path here. Okay. So just to make sure that so you see, let me just copy paste this quite a bit of times. Here. Another one, another one, another one. I will need another one. All right. So let's talk about the forward paths. Yeah, the place where the loop intersects, they do not, I mean, loops are intersecting here, for example. Here you see the loops are intersecting, but that's not a node. There is no connection here. It's an overlap, essentially. It's jumping out of that. So there is no connection here. Okay. So there is no connection here. No, there is no connection here. This is not a connection. Okay. Okay. So now that's one forward path. Got it. There is another forward path, in fact. Okay. You see that? Now, how many loops are there? How many loops are there? It's one loop. We took care of the gigantic loop first. There is one loop. Okay. See, this is not a loop. This part is not a loop. Okay. This is another loop. Okay. There is another loop. Okay. And there are other loops as well. Just hold on. Oh, sorry. Can I come back to this? Hold on. Yes, actually, I can come back to this. So that's another loop. All right, that's another loop. What else is a loop? Okay, I have another loop, right? All right, so these are all the possible loops here. So there are 5 loops and 2 forward paths. Okay, so this for this forward path, the gain M1 is G1, G2, G3. For this forward path, gain M2 is G1, G3, G4. Okay, for this loop, the gain is G1, G2, G3 and a -1. So essentially like that. For this loop, let's call this loop number 2. The gain is G1, sorry, G2, G3 and a -H3. For this loop, loop 3, the gain is 1 G2 minus H2, so minus G2 H2. And for this loop, the gain is, so this is loop 4, the gain is G4 G3, so G3 G4 and minus H3. And for loop 5, I have G1 G3, G4, and with a minus sign. All right. So these are all the possible loops, and that two forward paths are there. Got it? So now let's think about what the non-touching loops there are. So among these loops, which are non-touching? So L1, L2 are not non-touching, so they are touching. L2, L1, L3, L1 and L3 are touching. L2 and L3 are touching. L3 and L4 are also touching. L3 and all of the loops are touching actually, right? So all of the loops are touching each other. So there is no non-touching loop. So now we can say delta is 1 minus L1 plus L2 plus L3 plus L4 plus L5. Okay. So with that said, it is 1 minus all that minus G1, G2, G3 minus G1, G2, G3 minus G2, G3, H3 minus G2, H2 minus G3, G4, H3 minus G1, G3, G4. And that's obviously will be another copy paste. Get rid of this, and all of them are going to get plus signs. So 1 plus. All right. So that's the graph determinant. Okay. So now what about delta 1 and delta 2? Because since we have M1 and M2, two forward paths, I have to calculate delta 1 and delta 2. So let's calculate delta 1 and delta 2. So delta 1 would be the value of delta. Delta 1 would be equal to delta, considering only those loops which do not touch the first forward path. Okay. Considering only those loops which do not touch the first forward path. So this is the first forward path, if you recall. This was the first forward path, and all the loops are touching the first forward path. You see, there is not a single loop which does not touch the first forward path. So all these are getting cancelled for delta 1. So it is essentially equal to 1. Delta 2. So since all the loops touch the first forward path. Similarly, delta 2, all the loops, so this is the second forward path. Okay, this is the second forward path, and all the loops do touch the second forward path as well. So that way, so is there any loop which does not touch the second forward path? None. Okay, so that way this is also equal to 1. So therefore, the transfer function, which is C by R, is equal to M1 delta 1 plus M2 delta 2 divided by delta. Now what is M1 delta 1? I know delta 1, delta 2, both of them are 1. What is M1? G1, G2, G3. So this is G1, G2, G3 times 1. Of course, delta 1 is 1. M2 is G1, G3, G4. So that's G1, G3, G4. And divided by delta, and delta is of course this. Now, if you had done block diagram reduction to arrive at this result, then again, congratulations to you, but that took a lot of time, I guess. But we did this in 10 minutes, not even 10 minutes, in 9 minutes. Okay. You see, that's the, so again, I'm drawing all these things. If you can do this in your mind, that's again much better. All right, so that's the final result. So that's the block diagram reduced version. From signal flow graph, in a single step, you can actually calculate all these. Okay. So again, your homework remains your homework, and let me just introduce you to another homework. Okay. So I'm giving you a simple block diagram. You have to convert it to a equivalent signal flow graph, and from that you have to. So you cannot do block diagram. You can actually check with by doing block diagram reduction on this, but you need to do signal flow graph here. Okay, this is very simple example. So that's your exercise problem. Again, these are not connected. Keep in mind. Okay. So question is, draw an equivalent signal flow graph. And yes, regarding submission of homeworks, these problems would appear. I will ask you to actually do this at home. Okay, and these problems would appear in the Google Classroom. There you have to submit. Okay. So the question is, draw an equivalent SFG of the given block diagram and calculate the overall transfer function C by R using Mason's gain. Once again, this handout will be available in the Google Classroom as well as in the video description of this class. So that's it for today. If you have any question, any query, anything you might want to ask right now. Otherwise, we're going to end this discussion at this point. It might be a good idea to apply block diagram reduction on this, tally the result, okay, with the signal flow graph result. Because if you have done both of them correctly, you will go to end up with the same result. Okay, someone is saying arrow after this, so essentially arrow after G5, you can see that the signal is coming out of this, and okay, just that is okay, I made a mistake. Hold on. I made a very important. Yeah, thank you for figuring this out. I was supposed to draw this slightly different. Yes, you are correct about that. This is again not getting connected, huh? Okay, sorry. I am correct, I guess. Hold on. Just for a second. Hold on. It was correct, right? Yeah, it was correct. Yeah, it was correct. No issues there. It was correct. This is what I intended. Yeah, it was correct. See, the signal actually goes into this. So the arrow, if you really want an arrow, the arrow is this way. So the signal actually goes into this. So whatever signal that appears here is because of this. Okay, and these are all the tappings out of that. Okay, so essentially this signal is tapped from all that. So in other terms, you can actually draw this in a slightly better way, I guess. Could be less confusing. Okay, so let's tap it from here. Instead, let's tap it from here. Much better to actually see, I guess. Okay, so I think there is no confusion anymore. So whatever signal comes out of this actually goes in this way, and that is also tapped by these points here. All right. So that's the end of today's discussion. If you have any question, anything, any comment you want to make, please do it right now. We have already way over the scheduled time here. If you have any query, any comment, any concern, any question you might want to put, please put it right now. We are going to end the discussion. Thank you very much for being here for so long here. All right. Tomorrow we have the scheduled DAP class. There we're going to discuss a few things. In any case, so this is the end of today's discussion. All right. Thank you very much. I will see you tomorrow.